Good
Good
evening, ma'am.
evening, ma'am.
Good evening, guys.
Good evening,
How was
ma'am.
the group mentoring session?
It was good, ma'am.
It was good.
Good evening, ma'am.
Good evening, ma'am.
Good evening, everyone. Turn on your cameras, everyone. Only these many people. Where are the others? One or two, I'm expecting more. Turn on your cameras, everyone, quickly. Okay. So, yesterday we have discussed the Thomson model and the Rutherford model, right? And we had discussed the advantages and disadvantages of the same. Correct? Okay. So, all right. So the last thing that we ended at was the fact that disadvantage of Rutherford's model. Okay. The disadvantage is that if a charged species like the electron tends to revolve around the nucleus, then in order to maintain continuous motion, Fe is equal to Fm. Sorry, not Fm, but Fc. Centripetal force is equal to electrostatic force, right? But this was not actually told by Rutherford. We have, now we know it, so now we are capable of saying that, correct? Right? That's what we discussed yesterday. So, now before we move further to Bohr's model, I would like to little bit, dwell into some things like, let's say a charged electron. We all have read in class 10 that charged electron is a source of charged species like an electron, a source of electricity. And also when there is a changing electric field, then there is a magnetic field which is associated, right? Correct? We know this, that with a source of electricity comes magnetic field also. Yes? Correct?
Yes, ma'am.
Now, I want to ask that whenever we say that, there is electricity, there's electric power associated with this, there is magnetic field which is associated with this. So we can infer that these, particles, the subatomic particles like an like an electron, like a proton, they are nothing but sources of energy, correct? Correct? They are sources of energy. When we talk of the sources of energy, then what is the ultimate source of energy for us?
Sun.
Sun.
Sun. It's the sun, right? Correct. It's the ultimate source of energy. Now it must be emitting some energy forms, right? And they are coming towards into the earth, right? Only some part of sun's energy is allowed into the earth by the gaseous blanket which is surrounding the earth called the atmosphere, right? You know that atmosphere has various layers. There is stratosphere, there is thermosphere, there is ionosphere, right? So sun's energy, only a limited amount is allowed on the through the atmosphere. Okay, only a limited amount. Okay, Now we know that also from this we know that when sun's energy travels to Earth or various other planets, right? Does it need a medium to travel in?
No.
No, ma'am.
No, because outside there is vacuum, right? Correct. However, sound waves, they need a medium to travel in. Okay, you cannot hear anything in the space, right? These waves of energies, this form of energy, let's not categorize anything right now. This form of energy needs no medium to travel in. You know that this energy travels with a speed represented by c, which is 3 into 10 raised to power 8 meter per second, which we call as the speed of light. Correct? Right? All
Yes.
these waves. So this is speed of light. Correct? And they are transverse waves. Obviously, they are composed of atoms. Atoms are composed of uh, protons and electrons. And so that means they have an electrical component. Plus, they have a magnetic component. Right? Both are perpendicular to each other and also the direction of propagation. All right, both are perpendicular to each other and to the direction of propagation.
Can you scroll to the part of Rutherford's disadvantage in his model? I just missed.
Sorry, what?
Can you scroll to the part of Rutherford's disadvantage? I just missed. There's some lines to it.
It's not a clear-cut disadvantage because disadvantage would end at the fact that, if they do not balance each other, then they would the electrons would tend to collapse into the nucleus. Would not justify this. Bohr did. Okay.
Ma'am,
Yeah.
ma'am, can you please again explain the FE and FC part?
Yeah. Now, yesterday, has everybody noted this down?
Yes, ma'am.
This is noted. Yeah.
Yes, ma'am.
This is the electrostatic force of attraction. Yesterday, I had told you that every single body attracts every other body in the universe, right? By this universal law of gravitation. Yeah. So instead of this, we will have this 1 by 4 pi epsilon naught Q1, Q2 by R square. Instead of this is the electrostatic force of attraction. This will be equal to the centripetal force mv square by R. Q1,
Does silent knot mean?
I'll tell you this when we go to the Bohr's model. It is somewhat like it is analogous to this. It is known as permittivity in free space.
Okay.
Q2 is number of electrons. M is mass. V is velocity. R is radius. Now understood, Himanshu?
Yes, ma'am.
This is understood that all of these waves are, all of these energy carrying particles are having an electrical component, magnetic component, speed is this, they are transverse waves, right? And they do not need a medium to travel in. So out of the all the energy of the sun, whatever is able to travel to the earth, right? They are like this, X-rays, UV, gamma rays, UV rays, visible light, IR, microwaves, radio waves. Please note it down.
And what is after gamma rays?
UV rays.
Ma'am, what is IR?
Infrared.
Ma'am, and after microwaves?
Radio waves. Bachcha. Wait, I'll tell you. Can you see this? I think it's a little blurry. Wait. I don't know whether it's. Oh God, it is still blurry. Yeah, I think now it's clear. Yes.
Yes,
Now
ma'am.
it's more clearer, right? Yes. It's not
Yes.
getting blurry anymore.
Yes,
Okay.
ma'am.
Yes, ma'am.
Now, can you observe this just a little bit, enlarge it a little bit more till the time it starts to get a little. No, it's not getting blurry. That's amazing. That everybody can see, right?
Yes,
Yeah.
Yes,
ma'am.
ma'am.
Now, actually, if you see that diagram, and this diagram is a little bit gamma ray is drawn over here. I drew gamma ray on the left. It's just here and there. That's all. There's nothing much to worry about. Why? Because if you observe, then this is what we say, that this penetrates the Earth's atmosphere. This, all of these, right? These are the radiation type, and here they are telling you the frequency wavelength, right? Right. So just take it down. Just come. Just note this down.
Ma'am, what's the gray shaded area?
Yes, please.
Ma'am, for the penetrate Earth's atmosphere
Yes, ma'am.
category, there is YN in a gray shaded area. I'm assuming Y is
Some
yes
of it,
and no.
see, the thing is that not when we say that, some of the UV radiations are able to penetrate very well into the Earth's atmosphere. Some of the wavelengths are able to, some of the larger, higher wavelengths are not able to. Okay, fine. So that is, but we say that this whole range is there more or less. This is able to most of these wavelengths are able to penetrate into the Earth's atmosphere. And if you see this, the X-rays and gamma rays, most of them, the harmful ones, are absorbed at the thermosphere and the ionosphere part of the atmosphere. Okay, fine. They are not able to fully penetrate. All right. But if you observe the radio waves, then these are the waves due to which the signals are received. Right? Due to which you are able to listen to the radio. And visible portion is the only portion which is through which we can see, which we are able to visualize. The other things we are not even able to see. You cannot see the UV visible, you cannot see the UV radiations. And you must have heard the skin doctors say that stay away from UV radiations, apply sunscreen, this, that, right? You've heard about it correctly, right?
Yes, ma'am.
So
Yes.
Yes, ma'am.
some of it is able to penetrate, some of it is blocked. But due to continuous use of many chemicals, it is said that much more UV radiations are now penetrating from the atmosphere. Although it's not that we are directly exposed to X-rays, okay, that we are not, or gamma rays, no. Gamma rays we can produce through radioactive material. X-rays also, X-rays are unknown sources of radiations. Now, X-rays are used in treatment of bone, bone damage, right? And gamma rays are used to treat cancers. But it's not that you go out into the sun and these things are directly falling onto you. That's not true. Even some of the microwave radiations, that's not true that they are fully coming onto the surface of this earth. Otherwise, we would have been highly susceptible to skin cancers. Correct? So, have you heated something ever in a microwave?
Yes. Yes,
Yes,
ma'am.
ma'am.
Yes,
In
ma'am.
1 minute, it heats up the the food particles so much so that you can't directly put it in your mouth. Is it true?
Yes, ma'am.
Correct?
Yes,
It takes some time. So imagine if I tell you that the energy component, I'm just going to describe to you the energy component. Can you see the temperature over here?
Yes, ma'am.
Can you see
Yes,
the
ma'am.
temperature over here? But if you heat a particular object in microwave for 1 minute, you cannot even touch that object, right? You cannot even touch that food particle. Imagine what would happen if somebody was to get exposed to gamma rays or X-rays. That is why in hospitals you are told to stay away from the X-ray department, right? They will not allow you inside. Only the concerned people are allowed inside, right? So you can understand that they are not fully penetratable through the atmosphere. Got it? And the gamma rays are also obtained from the radioactive material. They are used to treat cancer. So imagine what a cancer patient would be going through, being exposed to gamma radiation. Because microwave heats up the food. And look at its position and look at its temperature. And gamma ray, what it would be doing to the body. Imagine. And what we think of ourselves, see, we can only see this part. And we think, Arey, we know everything. We are great scientists. We know a lot. We can only see in the visible region. You must understand, huh? We can only see in the visible region. Nothing else we can see. Now, infrared, those goggles are there. Have you seen? Night vision glasses, they have infrared, right? But still, I mean,
Yes, ma'am.
only some portion of the infrared you will be able to see, not much. Correct? Not all the way. Now, let me give you a formula which talks about the relationship of wavelength and frequency. E is equal to h nu.
I want to ask something.
Yeah, please.
I'm in this diagram. Why was microwave radiation's temperature negative?
Where? Where is it negative? It is nearly 1 Kelvin, beta. ऊपर देखो.
Minus 272 degrees Celsius.
See, it says temperature of objects at which the radiation is the most intense wavelength emitted. That they are talking about wavelength, temperature at which wavelength is emitted. That's what they are talking about. They are not talking about heating of an object. It's the emission of wavelength. I'll just tell you that also. It's not about heating an object in microwaves. No, it's the emission temperature.
Ma'am, for the penetration, when we are taking this down, for IR, are we going to write yes or no? Like they penetrate? Or
Which IR? What? Sorry.
ma'am, for infrared
Yeah,
radiation
partially. Yeah, partially. Yes, partially. Not fully, only
and for
partially.
microwave,
Yeah, partially, not fully. Most of it, no.
okay.
So nu is equal to C by lambda. So this is equal to HC by lambda. Nu bar is equal to 1 by lambda. So this is equal to HC nu bar. So nu is the frequency of a particular wave. Okay. C is the speed of the radiation, meter per second. Nu bar is the wave number, which is the inverse of the wavelength. Okay. And lambda is the wavelength.
Ma'am, what is the third one? Ma'am, what did you write for the third symbol? The one
Nu
with
bar.
the, yeah.
Nu bar. It is inverse of wavelength, 1 by lambda. Okay. And the unit of frequency, as you can see, it is second inverse. Okay. The unit of wavelength is meters, SI unit. Okay. Or second inverse, or after the founder Hendrik Hertz, the unit is named as Hertz. Got it clear?
Yes, ma'am.
So those waves which are traveling in a form of energy, they are represented like this. And in your NCRT, they are represented. I purposefully put this diagram because they are represented like this in the NCRT, right? Now you know that they have an electrical component and they have a magnetic component, and they are perpendicular to each other and to the direction of propagation, correct? Now, do you see any break in this? Do you see anywhere there is a break and then the thing is continuing? No, right?
No,
It's a
ma'am.
continuous range of frequencies or wavelengths. Also, one can see that energy is directly proportional to frequency. So can you see here energy frequency is increased? So energy or temperature is also increased. Now here energy is decreased. Now wavelength is very high in this case. Can you see? In your NCRT, you can see wavelength is so high. Look at this, wavelength is so low. It is inversely proportional to energy, right? From the formula also one can see is equal to hc by lambda. Yes. Okay, correct? Okay. Now, when we know that energy is equal to hc by lambda or h nu or hc nu bar, one can also see one more thing, that when we represent this, it is a continuous and such a continuous range is known as a spectrum. Spectrum. Spectrum is singular and spectra is plural.
And what does H stand for again?
Yeah, that's what I'm telling you. Hold it. So H here, when we know that everything else is a variable, can you see? C is a constant, nu is a variable, and lambda is also a variable. Let's talk about H. H is a constant. The value is please note this down.
Joule per second.
Sorry, what? It is what?
Is it, ma'am, Joule per second?
I can't hear you. What are you saying?
Ma'am, is it Joule per second?
Yeah, joule second, joule second. Not per second, joule second. Okay. Now, all of you, please open your NCRTs. Take out question number 2.3, I think so. Please do 2.1 and 2.2 as homework. Okay. 2.3 onwards, please take it out. 2.3, 2.4 and 2.5. I'll present also for you. If any one of you has a problem, please look at this. Can you please all of you do these questions without looking, of course? 3 questions, 3 minutes, quickly.
Ma'am, can you repeat the question?
Beta,
Number,
it's on the
question.
screen. Can you see the screen?
Yes, ma'am.
2.3 to 2.5, 2.3, 2.4, 2.5. Finish it, beta.
Okay.
Everybody should have their cameras on. Should not have to repeat it again and again. Every day it cannot be the same thing that you're not listening. Joyneel, Bhavyadeep, who is this? Izan, Yashvi. I don't know. I think this is your first class.
Till which question do we have to do?
All the three questions, 2.3, 2.4, and 2.5.
Okay, ma'am.
Ma'am, is it okay if I just take speed of light as 3 times 10 to the 8?
That's what
Like
you have
I
to take
should
it,
do.
right?
Yeah, okay.
Yes, I hope you're done. Please raise your hands if done. Yes, please. Done. Any issue, any problem over here? I think they're very straightforward questions. You don't need to do anything, right? Correct?
Yes, ma'am.
Okay. All right. I will, okay. Why some hands are not raised? Ashish, why are not able to do? Abhijay, Yuvraj, Manushri, Ashish and Abhijay not able to do. And Manushri, what about you?
Ma'am, it's just doing the calculations, taking time.
Okay, you can do them later. That's not a problem, right?
Ma'am, question number 2.4.
What happened there?
Ma'am, I don't know the question. I
You
don't
don't know
have
the
the
question?
textbook.
So you don't what? Sorry?
I don't have the textbook.
Please open it online. It's not a problem. I just showed it to you from there itself and do it, right?
Okay.
All right. All right. So I'll just present to all of you a situation. Let's say you and your family are wanting to eat chocolates. Okay. So there is you'll carry similar sized chocolate bars for each one of your family members, correct? Correct? To avoid any discrepancy, and then you'll say, okay, they're not their playing favorites. So you'll carry equal sized chocolate bars for every one of them, each one of them. Let's say the next day, your family members, they want to eat vanilla ice cream with chocolate syrup. Okay. So I want to ask you, are you going to give them still the chocolate bars or are you going to do something else? You'll carry chocolate syrup, not chocolate bars. Am I correct?
Yes, ma'am.
To be poured over the ice cream, right? So when you carried the chocolate bars versus when you had chocolate syrup, does it change the nature of chocolate, beta?
No, ma'am.
No. Does it change the taste of chocolate for you? No, it stays the same, right? Correct? But the form changes. Your perception of chocolate definitely changes. One time it was flowy when it was in the form of a chocolate syrup. The other time it was a firm bar in a particular shape, right? And that's how you had it. Am I correct here?
Yeah.
None of the properties of chocolate changed. Okay, chocolate is still the same. It is made from cocoa, right? It is not going to change. It is just a form is changed. Even that cocoa powder that you guys have, or so-called hot chocolate that we have in winters, right? So it still is like chocolate is made into a powder. Am I correct? Still, it has not changed. But I'm just talking about particular chocolate bars, and I'm talking about chocolate syrup. Correct? And let's say you have a bar of, so slightly that smallest part of dairy milk chocolate. You have that much. Have you seen that? Huh? Two squares are there in it.
Yes,
So
ma'am.
that much amount of syrup, if I convert, I'll be able to put it on a ice cream. Na? That's my perception of chocolate. So perception changes. Chocolate is the same. Okay. Now, if I tell you, similarly analogous situations you imagine. For example, there is a phenomena called diffraction and interference, right, which light shows. Versus, there is another phenomena which you can relate very easily, which is, hold on. So there's another phenomena which is you've seen on a very hot summer day, if you accidentally, if you park your car under the sun, right under the sun, there is no tree shade, or it's not a covered parking, right? So you can't even put your hand on the bonnet, right? You cannot do that. Your hands will get burnt. Okay. So that means the metal is sort of, the sun's rays are directly being put on the metal, and the metal is basically trying to, the longer the car stands in the sun, the more hotter the bonnet will get. Correct? So that means you are not perceiving light as a wave, rather as a particle. You are putting more and more and more and more and more particles. So it's getting more heated, more rise in temperature. There are a lot of memes and videos which are being shown. I can make a chapati on the car's bonnet. I can make a omelette on a car's bonnet. All those stupid memes are, coming, right? So that only means that, the heat of the sun is getting collected on the bonnet, correct? Whereas if I told you light is traveling in waves, if it was traveling in waves, nothing like this would have happened, correct? It would not have collected at one place. Again, does light change? No, light is just the same. My perception of looking at the light changes, correct? Similarly, when you had bars of chocolate, you brought multiples of one size. You had that one bar, and then you got it for each of your family member, let's say a family of 4. So you had multiples, 1, 2, 3, 4. You went to the shop and you got 4 bars. But if those 4 bars are melted into a chocolate syrup, that will be a whole bottle, right? From there, you can pour. Chocolate does not change, only perception changes. Light does not change, only perception changes. One time we say it's a particle nature, the other time we say it's a wave nature. It is dual nature based on our perception. Have you understood this thing? It is our perception. Light has not changed. Because we have to explain 2 phenomena, which is the various phenomena, some which are explained only by particle nature, some which are explained only by wave nature. I cannot explain some phenomena by particle nature at all. I cannot explain some phenomena by wave nature at all. That is a surety. Okay. But that does not change the fact that light is a transverse wave. It has an electrical component. It has a magnetic component. They are perpendicular to each other and to the direction of propagation. That energy is expressed by E is equal to hc by lambda. None of that changes. Everything is just the same. Do you get my point?
Yes.
Yes. So that has to be kept in your mind. Okay. Now let us talk about phenomena explained by wave nature. interference, diffraction. Explained by particle.
Ma'am, does that refraction also count?
Huh?
Refraction, doesn't it count as wave nature phenomena?
See, refraction is a bending of light. So that is not considering, that is obviously, that would be wave nature, but that is not confirming wave nature. See, because it's just bending of light. It's not joining of, it's not confirming a wave nature, right? But it's these two confirm, because interference can be constructive also, destructive also. Diffraction, the very famous diffraction slit experiment that you will study in, I think class 11th or class 12th, I think, in physics. Yeah. That when we say that refraction and reflection, when we say, yes, but see, if you consider reflection, part of it is when you consider concave mirrors, right? When you say that the light gets collected, that would be particle nature. But then bending of light at one point in time, when it crosses densities, it might end up heating a particular amount of water. So that does not, they do not conform to one nature, yeah? All right. But we need phenomena in which we can confirm certain natures of light, right? So this is heat capacity. Which we will study in thermodynamics. Photoelectric effect. Black body radiation. H atom spectrum. Let's go to first black body radiation. Can anyone tell me what is a black body? What do you understand by a black body?
Ma'am, a perfect emitter and absorber of heat and light.
Okay.
I think it
Can
was
you give me
just
an
light.
example?
Pretty sure a star is a black body.
How is a star a black body? How does it absorb all the radiations?
Ma'am, like black car absorbs more heat in summer.
What absorbs more heat?
A black car.
Um, so does it absorb all the radiations?
No, ma'am, but more than a white car.
No, that is
Ma'am,
that would just be a comparison, right? That would just be a comparison. That would not say that it is absorbing every single radiation, right?
Ma'am, perfect black body is theoretical as of now, not really achievable.
So you can write down a black body which is capable of absorbing and emitting
Ma'am, can sun be its example?
sorry
Sun can be its example.
but sun primarily it does not absorb every radiation, right? It rather emits because there is a reaction of two hydrogen and converting into helium, and then a lot of heat energy is emitted. Absorption would be when it ages off into a white dwarf. Then it would emit a lot, and then it would absorb a ton of radiation. That is there, but perfect black body is like a one which absorbs all kind of radiations they're gonna put on it, and then it emits also. So
Okay.
not just emitting, but absorption also. That also is required. Yeah.
Can black holes be considered?
Black holes only absorb, right? They do not emit.
Ma'am, theoretically, if we talk about white holes, then will black holes and white holes together act as a black body?
Yeah, but if that be, then you would have to combine both of them, right? It's like a similar question to what Johnny last. He said that, what kind of nature, is reflection and refraction. So you can explain that, incident radiation is there on a particular, mirror, and it's getting bounced off. Till that time, it is a wave. But what about a concave mirror where all the light is being focused and it is getting converted into heat energy? Correct? So primarily you can justify with one, nature, but not foolproof. Yes. So
Yes, ma'am.
perfect black body, do you think it exists? No.
No, ma'am.
There is no perfect black body on this universe. No. Maybe somewhere in the universe, but not here. Somewhere in the universe there is possibility because the universe is so vast. We have not explored entire thing, right? So one has to understand that such a body cannot exist primarily.
But we can prepare it in laboratory, I think.
Because all sorts of radiations are not available here on Earth also itself, right? That also would be just a range. You cannot have all the radiation sources here on Earth. No. Right? Even if you did, there would be some imperfections which would not allow, even if, like, let's say you managed to create a body which is absorbing all kinds of radiations, but there are definitely some imperfections in the packing structure of that body which will not allow it to absorb every single radiation beta. That is for sure. Because so a perfect body means perfect packing of the atoms in a particular structure. Now you will study in thermodynamics that there is no perfect crystalline structure. There is no perfect packing of a particular structure. No. Got it? That also you have to understand. So this is the reason why we say that there is no perfect black body, which is able to absorb and which is able to emit every kind of radiation. Yeah. So, you have to, one can imagine when we keep on heating an iron bar, first it becomes red, then yellow, then finally it becomes white. And slowly, when we stop heating it, all these radiations are also emitted. Right? So yes, it does absorb a wide range of radiations, but not all radiations again. Because, somewhere the bonds are going to break down, the object is going to melt. Right? So that also is there, that one has to consider. Okay, fine? Clear?
Ma'am.
Right. So we will continue with the graphical analysis of this and of black body radiation along with contributions of Max Planck in the next class. Tomorrow's class from 7 to 8 would be for the revision of the mole concept for all those people who have not attended or joined late. Okay, but if you wish to attend, all of you are welcome. I mean, it doesn't matter. Yeah, if you have time, you can. All right. So yes, thank you so much. On the count of 3, 2, 1, let's go. 3, 2, 1. Amazing. Thank you so much, each one of you. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Guys,
Thank
take
you,
care.
ma'am.
Bye, guys.